Hello, welcome. We are going to work on lesson 2.8 called linear functions models, and we're going to learn about variation. So let's go take a look at the notes that we have, the Google Notes here. So in the real world, most situations don't fit a perfect linear or quadratic or exponential model. And so when we look at the scatter plot of the data, it will say it looks linear, but not perfect. And so we're going to use Desmos to help us find the line of best fit. Now, this is explaining how to do it. I'm going to show you how to do it. The examples that we have in this lesson are perfect. They are going to work out perfectly because we only have 2 points, and 2 points to create a line will create a perfect line. But I want you to know how to do this in Desmos so that you can kind of shortcut creating a line yourself. So when you go into Desmos, you're going to click the plus sign and choose a table. And then you're going to enter your data into X1 and Y1. So your X1 will be your independent variable. And your Y1 will be your dependent variable. Then you're going to click on the magnifying glass at the lower left so that the graph will make the correct scaling for your data. Then in the new line, type Y1 and then this tilde symbol. Make sure you don't use an equal sign. Type the tilde and then mx1 plus b. This will create the line of best fit for your data. And the m will be your slope, that's down here, number 6, and the b will be your y-intercept. And then our hope is that our r squared, that's going to come out, I'll show you in a minute, in Desmos, will be a perfect 1. In this case, it will be because the line fits 100% of the data, but we really want it to be greater, we want that to be greater than 0.8 for the best fit. So let's look at our first example. Let's get our data ready, and then we're going to go to Desmos and try our first one. So it says, if 32 degrees Fahrenheit corresponds to 0 degrees Celsius and 212 degrees Fahrenheit corresponds to 100 degrees Celsius, find a linear function that converts a Fahrenheit to a Celsius temperature. So Fahrenheit is going to be our independent and Celsius is going to be our dependent variable. And I'm going to show you how I put these values on my paper here. So I have 32 degrees Fahrenheit and 0 degrees Celsius are my X and my Y, and then my other one is 212 and 100. So we're going to go into Desmos and put 32 and 212 in X1, and then 0 and 100 into Y1, and we're going to find the equation. Okay. So I'm going to click on the plus sign. And let's just don't need that. We're going to save this. Desmos for 2.8. And we're going to just note this is Fahrenheit to Celsius. Okay, so I'm going to click the plus symbol and I'm going to say table. And then in X1, I'm going to put 32 and 212. And I'm going to go over and put 0 and 100. And like I mentioned, I'm going to click my magnifying glass and it shows me the 2 points. You can see them on the graph. There's one down here where my mouse is on the x-axis. And then there's the other one up here on the right, top right. Okay, so now in the third line, I'm going to type Y1, and I'm using Y1 because my data is in Y1, and then the tilde symbol, MX1 plus B. And you can see that R squared is a 1 because it's a perfect fit for, the line is a perfect fit for my data. Most times it won't be. And then my parameters are my slope and my y-intercept. So my slope is 0.5555, so 0.56, and then my y-intercept is a negative 17.78. So we're going to write this on our paper here. So we have 0.56x plus a negative 17.78, or you could have minus 17.78. So I'm going to show you my paper so you can see how I wrote it and how you would want to write it. And this is the slope, and that's the y-intercept. Okay. So we're going to use the modeling for linear equations today. Then the second piece that we're going to look at today is variation, and we're going to look at direct variation and inverse variation. Direct variation is when a model gives rise to a linear function of the form f of x equals k times x or y equals k times x. Notice that there's no y-intercept. The y-intercept is at 0. And then your k is essentially your slope. The k in this case is called the constant of variation. Just like your slope is called your constant rate of change, this is similar to that. So we want to be able to find out what that constant of variation is, because they're going to give us a scenario for x and y. So number 11 says, let y vary directly as x. And that tells you when y varies directly as x, that we're going to set it up in this form, y equals kx. And then when y equals 35 and x equals 10, find k. So I have this question set up. Because it said it varies directly, I'm going to use this setup, y equals kx. And then they gave me y equals 35 and x equals 10. So by dividing by 10, we can find out what k is. So k is 3.5. They asked me just for k, but I like to also write out my actual equation once I get k. So let's go look at the other type of variation. Oh, we have another fun one. So number 27 in the book says, the volume of a gas varies directly. So again, it told us it was varying directly with the temperature. So the volume varies directly with temperature. Find K if the volume is 50 cc's at 40 degrees Celsius. Then after we do that, they're asking us to go a step further. And what is the volume of the temperature if the temperature is 60 degrees Celsius? Okay, so let's go ahead. I've got some things written on my paper here. So this is what they told us. Volume is varying directly with time. With temperature. With temperature. And we need to figure out what the constant of variation is. So at 50 cc's is my volume when I'm at 40 degrees Celsius. So K is equal to 55 divided by 40. And so K equals 1.375. And because it's a terminating decimal, let's use that whole thing. So Y equals 1.375x. We know that this is going to be our equation once we know K. And it says, what is the volume when the temperature is 60 degrees Celsius? Okay, so we want to know the volume when the temperature is 60 degrees. So we can multiply by 1.375, and our volume is 82.55 cc's. Now, the other type of variation that we're going to look at is called inverse variation. And that definition is here in our notes. It says, when a model gives rise to a linear function of the form f of x equal to k over x. So this time when x goes up, y goes down. Before, when we had direct variation, when x goes up, y also goes up. Okay, so inverse means they go in opposite directions. So a basic one is number 13. It says let y vary inversely. So when it says inversely, we know that we're using this format up here. You can either use k over x, or you can say y equals xk. Xy equals k. That's what that's supposed to be. So okay, so let's go and look at this one on my paper here. So we know it's varying inversely. And we know that y is 2.5 when x is 6. And so for us to solve for x, we're going to multiply both sides by 6. So I'm going to multiply by 6, multiply by 6. And we're going to find out our constant of variation. That k is called the constant of variation, or the constant of proportionality. And that comes out to be 15. So that means my equation would actually be y equals 15 divided by x. We have another fun problem to look at. So it says number 32, we're going to look at next in the book. It says the time t required to drive a fixed distance varies inversely. So that tells us what setup we're going to use as the speed of the car. So distance, the time t required to drive a distance. So the time is inversely related to the speed. If it takes 2 hours to drive from New York to Philadelphia at a speed of 55 miles per hour, how long will it take to drive the same route at a speed of 50 miles per hour? Let's check it out here. So we said that time is inversely related to speed. And we know that 55 miles an hour, we made it there in 2 hours. So if we want to solve for k, we're going to multiply both sides by 55. And that will make k 110. So our equation is y equals 110 divided by x. So it says how long to drive the route at 15 miles per hour. So y is time. So 110 divided by 50 is about 2.2 hours. So it's going to take us 0.2 of an hour longer if we only drive 50 miles an hour. Okay, the last problem for this lesson is number 41 from the book. It says in 2007, the average weekday volume of traffic on a particular stretch of the Princess Parkway was 175,000 vehicles. By 2011, the volume had increased to 200,000 per weekday. By how much did the traffic increase per year? Mathematically, what does this quantity represent? So how much does it increase per year? So we could do this by hand. We've done some by hand, but I want to see it practice in Desmos. So I'm going to show you how I would think about this in Desmos. So I'm gonna just make a note for us here. This is number 41. And I'm gonna make a table. And notice that my table now is X2, Y2, because I have a table up here that I have X1 and Y1, and I'm just gonna unshade those. So X2, Y2. So let's go back to the notes. It says in 2007, now it does not give us a start year where everything's based off of, so we're gonna use 2007 as our base year. So that means 2007 is gonna be 0. And so 2011 is gonna be 2011 minus 2007 should be 4 years. So that's going to be 4 years. And in 2007, there were 175,000 vehicles. And then in 4 years later, there were 200,000 vehicles. Okay. So I want to come up with a model for this. So since my data is in X2 and Y2, I have to refer to X2 and Y2. So Y2 tilde MX2 plus B. And voila, there's my equation. Again, because there's only 2 points, it's a perfect fit. Our R squared is 1. And I didn't hit my magnifying glass, so let's do that. And there it shows our 2 points and the line that goes through it. And what's cool is, look at, I can grab the slider on the graph and I can find any point that's on the graph. It's so cool. I can find the y-intercept there, and I can find the x-intercept if I want. Oops. Pretty close. I can get close. I just have to. Oh, it's way down here. That's why. Here it is. Okay. So M is 6,250 and B is 175,000. So let's just write that down. Y equals 6250x plus 175,000. And A says, by how much did the traffic increase per year? Well, that increase per year is our average rate of change. So average rate of change, which we did earlier in chapter 2, is equal to our slope, which is M, and that's 6,250 cars per year. That is increasing. So I'm going to share my paper so you can see that. So it's increasing the number of cars per year is increasing by 6,250. Then question B was asking us, create a linear model for the volume of traffic as a function of time and use it to determine the average weekday traffic flow for 2013. So we have the equation, y equals 6,250x plus 175,000. And we want to know how many average how many vehicles on an average weekday will there be in 2013? So if we go to Desmos here, 2013 minus 2007, because that was our base year, is 6 years. So X equals 6. So I can go to my slider here, and I can find when X equals 6 right there. So X equals 6. There's going to be 212,500 vehicles. That's what we predict. We predict 212,500 vehicles in 2013. Now, if we really wanted to find out, we could go back and research that. I'm sure that data has been collected somewhere. So that's all I have for lesson 2.8. We've completed chapter 2, so you can start reviewing chapter 2 and get ready to move on to chapter 3.